Hello and welcome. I'm so excited to have with me battery experts from the Honeywell team today. I'm Jill Pestana, your host. I'm a battery scientist and engineer, founder of Pestana Solutions, and we're about to talk about battery quality. So first, as we get into this, let us know in the comments, where are you tuning in from? And what are you hoping to learn about battery quality? So we have Alec Falzone here. Alec is the America's battery industry leader at Honeywell, based in Houston, Texas, with a PhD in inorganic chemistry from NC State. And Alex has led programs in electrolyte and polymer development and qualification of DoD battery systems. At Honeywell, he drives the adoption of advanced digitalization, inline measurement, and process control technologies across the battery industry. And JR with us is a battery manufacturing expert at Honeywell, and she specializes in lithium-ion and lithium metal technologies. She leads efforts to enhance quality, yield, and reliability across production. Formerly at General Motors, JR managed international battery projects and helped scale emerging manufacturing technologies. With multiple patents, JR brings deep technical insight to advancing energy storage innovation. Welcome, Alec and JR.
Thanks, Jill. Excited to have a really good discussion today on quality and battery cell manufacturing and anything related.
All the good stuff.
Happy to be
So,
here.
yeah, so please, everyone tuning in, ask any questions in the chat and we will respond to them at the end. So, when you are starting up a battery manufacturing plant, you really need to consider and manage risks to your operations. An issue with your cell quality can really impact the success of your company. And we'll be talking about all of that today in our webinar, Tackling the Cost of Poor Quality with Process Traceability from Powder to Pack. In this agenda today, we will cover the hidden cost of cell defects, the ROI of proactive quality control, process level traceability, where traceability falls short. We'll touch on global standards and compliance, and then talk about what we see in the future outlook, and have that Q&A. So what challenges, JR, are we seeing across the battery value chain, from raw materials to production to in-use applications today when it comes to battery cell quality?
Wonderful. Good question, Jill. So everyone is having very similar difficulties with controlling the manufacturing process. Finding your perfect recipe, your perfect design is the beginning step, but then actually controlling all of the steps of manufacturing is quite difficult because there are multiple steps and they all have many inputs that any small change in any one input can affect the quality. So manufacturing batteries is actually one of the most difficult manufacturing processes that there are, because these little electrochemical systems react to everything. So everyone has these difficulties with process quality control. Especially after the fact, that turns into performance difficulties with the battery later on. Eventually, sometimes it can lead to recalls if they're significant. So these are the things that manufacturers care about the most. And each step in quality control, if we try to make it go faster, then those little defects build up faster. So doing that quality control for every step of the process at slow speed, and then as we speed up to faster speed, making sure it stays in control as we go faster.
Right. It's not just about going slow, coddling the cells, making sure they're produced well. It's about how can you scale up production and get to that gigafactory level. Alec, do you have any thoughts to these challenges?
Yeah, so I like how JR mentioned that manufacturing a battery cell is extremely difficult. So if you think about a cell, I like using the analogy of the cell isn't a static widget. It really is a living, breathing thing where after it's manufactured, things change over time, and batteries last a long time. That's why quality is so difficult, is, any sort of manufacturing process, it's always challenging to stay within specifications and meeting quality specs all the time. And it's even exponentially more difficult when that thing you're manufacturing is dynamic over its lifespan. So kind of having robust things in place anytime something new is introduced, whether it's a new material or a new process technology, kind of introduces, more degrees of freedom, more, opportunity for challenges. So I think the challenges we'll see today are different than the challenges we see tomorrow. And that's why kind of having a very robust approach to quality is so important.
Wow, yes. And you're right. Batteries are so dynamic. There's so much to the process. And let's get into the Gigafactory project journey. From when you're first starting out through the project life cycle, this can take years. And Alec, tell us more about what companies can do to set themselves up for success, or what challenges they're having in the beginning.
Yeah, if you think about the journey of a battery manufacturing plant, it's not that much different than any other capital project, whether it's automobile manufacturing or a chemical refinery or things like that. So for battery manufacturing, there's always the upfront design. You think about, what do I want to make? What's going to go into the thing that I'm going to make? Where am I going to source my components from? How will I qualify them? All of that's done early on. You can think of that as the conceptualization phase. And so after that's done, usually there's a second phase where you start piloting either at your own facility or maybe a partner facility, right? And that's really the basis for your large scale gigafactory or megafactory or whatever scale you'll be manufacturing at. But at some point, you finalize all of that and there's a design freeze, and then you make your final investment decision. So after that, you have investors, you have stakeholders, you have a robust team in place that's going to help execute the plan. And then you start procurement, you start construction, you start groundbreaking, you start getting equipment on site later on, and then you start the commissioning of that equipment. And so that's really what you're seeing on the screen here, is that upfront planning takes a while, right? And the more proactive you are in that early phase before procurement and construction starts, the easier and kind of smoother that kind of ramp up phase is going to be. So the objective is always, how can I, start production as soon as possible? How do I de-risk my project? And so you de-risk the project by being more proactive, by relying on experts, partners you bring in to help, execute your capital project. And part of this commissioning phase, you do start your initial production runs. And so as part of that, you're using resources, you're using material you bought, you're burning through the investment dollars that you need to execute the plan. And that's where you kind of venture below your break-even point, and you kind of venture through what some call a valley of despair. And the objective is to sprint through that valley as soon as you can, right, to get to your break-even point. But to your point, Jill, it takes years, right? And maybe it's 2, maybe it's 4, maybe it's 7, right? The objective is to go from 7 to 5, and 7 to 4. And I think throughout today's discussion, we'll talk about a few specifics on ways to do that.
I thank you so much for summing that up. Yeah, the valley of despair. Oh my goodness. We want these projects to succeed at the end of the day. Like, we need battery technology. There's a huge demand. So let's talk about what causes companies to stumble a bit during that valley of despair. And definitely want to highlight defects, the role of cell level defects. So what is a cell defect?
Yeah, so as part of the ramp up phase, right, you always have your parameters you're trying to meet, right? And so, you occur a defect, whether it's a physical defect or a performance defect, and those defects are introduced along the way of manufacturing. It could come from the raw material on the inbound side, or it could come from a piece of machinery that deviates out of calibration. So you never know where the defect is going to come from. And again, it could be physical or it could be performance. Maybe physically it's fine, but it doesn't meet your capacity specification. It doesn't meet your charge or discharge requirements. That's another type of defect, right? So there's no shortage of anomalies and where they come from.
Yeah, JR, what are different types of cell defects?
Great question. So when we think about defects, we're going to put them into 4 categories. We're going to say there's material defects, there are design defects, there are equipment defects, and then there's process defects. So when we first design our cell, we can figure out what's the material, what's the design, and then of course we have IPQC, in-process quality control, and IQC, incoming quality control, where we do that incoming quality to make sure there's no defect in the material. And then once we get to the process, that's where we're going to start doing IPQC, where it's in-process quality control. So with these defects, there's a severe defect, which can lead to your internal shorts, like hard shorts. And then there are latent defects, which they don't show up in the IPQC and the in-process quality control. And they only really show up afterwards, after the cell has started working in the field. So it's when the cell charges and discharges, it's going to expand and contract. And what was a little defect now turns into a big defect. So we call those latent defects. So our hard defects, or hard short defects, our major defects are things like folded separators, holes or tears in your separator, metal contamination, and or electrode burrs, where it's little shards of metal that get stuck in there and then they cut their way through the electrode. If you have really badly misaligned electrodes, that sort of thing, or you don't have enough insulation on your cathode tab, that kind of thing, those are very serious defects, and we can catch those in the IPQC, in the in-process quality control. But the latent defects, they're a lot harder to catch because they're small. The cell hasn't moved around yet as it's expanded and contracted, and so they might not be caught. So small misalignments or things like agglomeration in coatings or non-uniform coating thickness, these are things that we have to add in lots of extra quality control to catch them, because it might be just one little spot. And then we also want to make sure we add more tests later to catch each little defect as it goes and hopefully catch it before it leaves the factory. So those are the sorts of defects we think about, you know, from the top down, from the cell as it goes through its life cycle, and then as it leaves and it becomes an active cell, as Alec said, living and breathing and moving, and growing over time or aging over time.
Wow, you know, it's very obvious that, okay, as you're manufacturing a cell, it could be defective, but the latent defect topic, that's like a hidden secret that, you know, that could blow up big and cause a lot of problems. You know, when we were talking about this, we were talking about failures could be like an ultrasonic welding failure leading to high DCIR or failed tab welding, but a latent defect, what are some examples of those?
So a really important one might be water contamination. Just a little bit of water contamination, it will autocatalyze into HF, but over time it gets worse and worse, and then it causes corrosion, and then, you know, it starts gassing, and then it can just get carried away. But you might not notice it until much later because it hasn't had time to react. Another latent defect might be the misaligned electrodes. You know, as the cell expands and contracts, what was a slight misalignment becomes more misalignment. There's many, many latent defects. Other things like, there's tons of latent defects.
Yeah.
We'll put misaligned electrodes as a good one. So.
Yeah, and I feel like being a battery scientist, a lot of times you just don't know. Like, it's hard to really pinpoint that.
Well, yeah. Well, I mean, we've got huge lists, but yeah, catching it, that's we want to catch it. Like, that's
Catching it. Yes,
yeah.
yes. And so when we're talking about like the impact of a latent defect, we really need to think about not just how it could affect, okay, you produce a cell, it's bad, you scrap it, you recycle it, you know, but what happens when there's a latent defect in the field? What kind of implications does that have down the line if something bad happens?
Yeah, there's so many, you know, things that could happen in the field as a result. So if you think about, you know, how the latent defect manifests itself really depends on the end use application. So if you think about if the latent defect ends up in an electric vehicle, whether it's hybrid or battery electric, you know, a car, you know, has a suspension system, but there's constant vibration, there's constant temperature fluctuations. And so if it's mechanically related, like a misaligned electrode, the more you vibrate something, again, there's pack design things that are designed to kind of compensate for these things, but over a 10-year lifespan, you know, eventually it'll show itself, right? But the example, we wanted to walk through was a battery energy storage system. So while it's not a moving vehicle, it's very similar. So if you're not familiar, a battery energy storage system, a lot of times are containerized, where it's like a metallic and painted shell. And then inside of the container is a massive battery pack, to think about it that way. And the battery pack is a battery management system. It's comprised of modules, right? There's usually a fire protection system. There's usually an environmental control system, heating and cooling, whether it's liquid or air. And then there's usually a remote monitoring system, because these are usually out, in the field, with not a lot of people around. So there's usually a way to monitor how things are performing. And so a very real use case of how a latent defect manifests itself in an ESS is a premature module failure. And there's maybe two categories or two buckets it can go into. One is the latent defect results in a catastrophic short circuit that results in a fire. And that fire will trigger the fire protection system. It'll be detected. There's usually a fire suppression system, whether it's wet or inert gas or something else. And then the fire department's notified. And, there's a response to the fire event. But if it's not a catastrophic safety event, let's say it's just performance. So you have modules that prematurely fail because a series of cells start to fail early as a result of misaligned electrodes, or the result of cathode dissolution from HF in the cell, or from something else, right? Cells fail for a lot of reasons. And so those modules fail. And what does that mean to the operator of the energy storage system? Well, they can't meet the performance. And so a lot of these ESS systems are supporting the grid to mitigate brownouts, or, kind of supplement the electricity capacity in the region. Or, they have to also last a certain amount of time. And so the warranty periods for ESS are usually 5 to 10 to maybe even longer years. And so the provider of the ESS is responsible for ensuring performance is met over the warranty period. So if modules fail in the field, they then have to go out and replace a module, multiple modules, and then again perform, specification testing in the field to make sure the replacement did what it was supposed to do. And at the end of the day, these are increased costs to the provider of the battery energy storage system. And then it's also not meeting the end customer requirements for performance. So if you think if you buy something and it doesn't, you can't use it how you intended to, that's not a great scenario. And so latent defects have, again, it could be a catastrophic event, or it could just be a, performance issue.
Yes. And there's also just like that latent defect, it wears out the other batteries. So if one of them's failing, then the other ones have to compensate, and then they wear out faster too. So that's a cascading effect. And then you've also got just the electronics. So we'll say the electronics are getting overloaded with extra electricity, and it starts to burn out the electronics. So you might end up, even if it's just a slow system, it could slowly be burning out your electronics as well.
It's like having to work harder to compensate for the defect over time. And yeah, when you buy an energy storage system, you calculate your total cost of ownership and really rely on those numbers to say, I'm assuming my cells are going to function for the lifetime, but that latent defect can sneak up on you. So when we're thinking about preventing these defects now during production, as well as these latent defects, like you're going to be spending a lot of money to make sure that you're producing quality cells, right? And you're going to be paying, right? The implications of your company running to the issue because of a cell defect are just so much higher of a cost. And this table shows that financial impact at different stages. So both in putting in prevention measures, in if there's a failure to produce quality cells, or in the field when the device with the cell is operational. So these are both proactive ways to respond and reactive ways to respond. And I think we all want to be more proactive with how we respond to quality. And these four main categories are where costs arise that we've mapped out here. So there's the prevention costs, the appraisal costs, the internal failure costs, and the external failure cost. So what hidden costs do teams often overlook beyond, say, warranty or scrap?
Yeah, so I think you put it nicely where the more proactive you are, I think the less reactive events you experience down the road, right? So if you think back to the capital project journey and de-risking, the more proactive and more robust quality systems that are planned early on, they may incur a higher upfront investment, right? You're just requiring more things to be implemented. But over the life cycle, your total cost of ownership goes down, right? Because you are de-risking, you are mitigating quality events down the road. So the more or the earlier you're detecting some of these things, you can react in real time to make changes to improve quality, which reduces the amount of rework you have, which is that third category, right? Which reduces the amount of offline root cause analysis that has to be done because you mitigate a lot of those events, which in turn you have less quality escapes resulting in field replacements. So it really is a compounding effect that it's not always a hidden cost, but overlooked costs. And so while early upfront planning and investment, it's always a dynamic discussion. Do we spend now or do we just kind of do what we can and we'll do things later? It's always a different decision, depending on the unique scenario, but kind of getting in the mindset of being more proactive helps kind of reveal these costs sooner than later.
Yeah, JR, what are your thoughts on making sure that, it's not causing a lot of cost for a latent defect?
Yeah, so as Alec was saying, there's the process costs of each step costs money. So the sooner we catch it, the less money we're spending on that next step. So if we think about the process, even if we get to the end, if we have, batteries in storage, just paying for that storage warehouse, that costs money. Or the transport of transporting to a waste landfill or to hopefully a recycler, that costs money. Or the process of actually recycling, that costs money. So there's that storage cost, the transport costs, and then each process step costs a little bit more money. So like, for example, the electrolyte, if we catch it before electrolyte fill, electrolyte's very expensive. So we save a lot of money by not putting expensive electrolyte into a bad cell. But then let's say maybe it's the formation process. The formation process, we're charging the cell, so we're adding electricity, we're adding cost because we have to pay for that eventually. So again, there's the cost of charging it. So each step costs more money. So we save money by catching it sooner, as he said. And then there's also the people. So if we think about the hidden cost of people, there's the time of that engineer having to, fix that problem over and over again, or having to fix this problem, which then reveals the next problem, and then they have to fix that problem. So we have more people spending time fixing problems instead of spending time manufacturing batteries. My favorite example is process operators who are afraid to tell the boss that something's broken because they're afraid that they're going to get blamed. And I've seen that. And so it's difficult because they don't want to say it, but they know that it's happening. However, if we had a sensor there measuring the process, then the boss or the engineer can see, oh, this happens on a regular basis. It's nothing to do with the operator. It's nothing to do even with the material going through. It's happening every 2 weeks. So it must be a machine malfunction. Maybe we need maintenance. So in that kind of scenario, if things had been automated, then we would have removed the emotions of the people and we would have solved the problem quickly.
Yeah, it's like you could have a bunch of data, right? But what are you doing with that data? How are you making smart decisions? How are you catching this? Like you said before, electrolyte fill. Because yeah, electrolytes are super expensive. So yeah, catching it before then saves you all this headache and the storage costs and the labor costs. It like snowballs up the more that you wait to find that defect. So that early detection right when it starts seems to be the right approach to save, because like catastrophic failures in the field that could cause recalls and tank your reputation as a business. And we've seen that happen before. And that is not what you want to get to. So that upfront investment seems very much worth the effort and a necessary part to consider when you're considering your OPEX and CapEx costs, right? And thinking about, oh, do you want to add anything else, JR?
I was going to say that old saying, a pound of, or an ounce of prevention is worth a pound of cure, something like that. Yeah.
That's cute. I like that. Yeah, and when we're thinking about the cost of quality, as the cost scale, like, or sorry, my question is, how do the cost scale as production ramps up? I butchered that question.
Yeah. So using the example of the electrolyte fill, because I like that example, right? Because you can put good electrolyte in a bad cell, or you could put bad electrolyte in a good cell. So if you think about early on in the process, the cheapest scrap you can have in any factory is the raw material, because you haven't added any value to the raw material. You haven't spent, people's time. You haven't spent resources with utilities or time in the machine. You haven't started that work in progress of transforming that raw material. And so if you can, for inbound QA/QC of electrolyte, for example, if you have 150 ppm of water when your spec is 10 ppm, do not let that electrolyte be put in the fill, right? If your cathode particles don't have the right morphology or size, don't introduce that to the mix, because if you scrap it in the mixer, the cost of scrapping that versus the raw powder is higher, right? And so then you think about the mix, you're continuously adding value at each production stage. So it's cheaper to scrap raw material than it is in mixing, than it is of the coated electrode, than it is of the wound jelly roll, than it is of the sealed can. So that's kind of what this graph is depicting, is the earlier you can either remove or correct the issue, it is a much, much lower financial impact. And then once it gets into the end product that is shipped to the end customer, whether it's a consumer or somebody who's manufacturing a vehicle or an energy storage system, if it fails at the pack level, that is absolutely, not a great scenario, right? No. So it's, again, powder is better than mix, then is better than cell, that's better than pack, that's much better than the end product itself.
Absolutely, that makes a lot of sense. Yeah, and I love how these graphs really show that exponential curve, right? Once you get to that litigation phase, like that's not something you want to be spending your money on, right? And when we're thinking about now some real concrete examples, I would love to share, if you could share an example of the importance of quality control early in the process, so you're not compounding costs and risks when the battery is released into the wild.
Yeah, absolutely. I think, one example we put together is in manufacturing, right? There's different measurement points in the manufacturing process. One of the most robust pieces of quality in the process is end-of-line testing, right? Where the battery's been manufactured, the end-of-line testing results are really the performance specifications that you've agreed to with the end customer. So that's where capacity is established, rate capability, the physical dimensions, all of those things, right? So end-of-line testing is critical. However, if you're relying on end-of-line testing to capture all quality events, that should really be the last line of defense. So there should be more quality and measurement systems in place well before the end-of-line testing area. So the more measurement you have, the more ability to control you have. You can reduce variability. You can ensure you stay within the process specifications, right? So that when you do get to end-of-line testing, everything passes. But if you're relying on end-of-line testing to catch everything, you result in a large batch of cells in quarantine. And that's what you see here. So this is a very real use case of, let's say you have 10,000 LFP prismatic cells that failed end-of-line testing. There was really minimal things in place upstream. And so those cells are now in quarantine. So all you know at this point is it's failed your open circuit voltage, it's failed AC internal resistance, it's failed DC internal resistance, and there's an unknown root cause. So what you then do is open a quality audit. So every company has a quality program. So you start a quality audit to determine the root cause analysis. And usually in this case, there's some offline things that have to be done. You know, a statistical amount of those cells are sent into the lab for offline testing. But again, that's spending people's time, it's spending resources. You have to wait for the results. You know, things aren't, you know, things don't happen like they do in CSI so quickly. You know, it takes days to get results from the lab, right? And once you have the results, you have to analyze them and then determine where in the process that deviation occurred, and then ultimately implement a corrective action. So you have to determine the root cause, determine as a team what the corrective action needs to be. You have to document the corrective action. Then you implement the corrective action. And then you update procedures and policies and train people. And there's a lot that goes into it. All the while, you may have produced 5, 7, 10 additional batches before these corrective actions are put in place. And so not only do you have 10,000 cells in quarantine, now you have more cells in quarantine that were produced potentially with the same defect. Maybe those cells are okay, but you have to do additional checks, because after you detect a quality deviation, you have to ensure the batches that came after that batch in quarantine don't have the same issues. And so, you know, these have millions of dollars of financial impact, and that's kind of, you know, some, you know, numbers we put together. So again, kind of at the bottom of the slide, just kind of graphically depicts this. And so you want to be more proactive, you want to scrap things sooner than relying on end-of-line test to be your catch-all for quality systems. So, you know, detecting it earlier in the process is better than catching it at end-of-line testing, which is still better than catching it in the field and dealing with warranty claims and potential litigation. But at the end of the day, all of these scenarios incur a loss in financials. You just try to minimize that number as much as you can.
Wow, yes. I love this example, and you're so right. I think there is a bias towards leaning on that end of line finishing formation where you're getting certain checks, but if you're waiting that long, you're already you've already produced a cell that's bad, and then you know that, yeah, it's going to be more expensive. Like, JR, do you have any thoughts on this case study?
Yeah, I was going to say, I think the way this happened just from the history is that people who were manufacturing other goods that were less complicated or less sensitive sort of applied that mentality to battery manufacturing. And so for them, maybe, you know, they're making metal pieces. The metal piece, if it sits there for 2 weeks, is not necessarily going to become explosive. Whereas the battery, if it sits there in the heat for 2 weeks, it might become explosive. So it's sort of like that mentality passed over, and so people need to go back and say, okay, we need to put more checks in. It's a black box. The cell is a mystery, and you really got to test it and at every single step to make sure it is what you think it is.
Absolutely. And you probably don't even want to be shipping it somewhere to be tests at end of line, because what if there's something wrong in the logistics and transport? I know there's certain like quality standards you have to meet even to transport cells, but it makes you think, yes, we can't do what we do for other devices that aren't going to be as volatile as a battery could be if there is something wrong with it, a defect or something. So what ROI have you seen from implementing traceability solutions?
Okay, so the rule of thumb in industry is it's like a 3-year return on investment. Everything has to have 3-year return on investment. It's not like buying a house where you pay it off in 20 years. You got to do it in 3 years. And for a lot of some quality stuff, they want even shorter. They want 6 months or a year. But we see massive changes. So as soon as somebody starts measuring it, what gets measured gets done. So the actual ROI can be, 100%. 1,000%. Just it depends on what type of sensor and what kind of defect they had, but almost always it's quite instant. So
Yeah.
Almost always.
Yeah, you really see that difference when you're investing in the right kinds of solutions. And what's the best way to frame, okay, we need to invest in these quality solutions early in the production process to really catch something along the line? Like, what do you think to justify this investment? Because it is an investment.
Yeah, it is. I think, you think about the cell manufacturing process, and if you have an existing facility, you have this historical data to where your individual process step yields. And so maybe you've been operating your plant for 5 to 10 years, mixing has, 95% yield, for example. And that coating, it's more difficult. So maybe your electrode coating yield is 70%. It's still pretty good, but there's room for improvement. And so based on that, your cost for each production stage. And so, if you look at implementing, a quality control system, right, more measurement, more control, you can then do a calculation, and partners like us at Honeywell can help you do this, right? And you can take the yield from 70 to 80, and you can put real dollars to that. And so ROI, like JR mentioned, because manufacturing a cell is very expensive, so ROI is typically not years, it's usually months. Within 12-month period, we see is well within reality.
Yeah, reaching that break-even point as soon as possible. You're right. You see it in the time, perhaps, too. And so to address defects, so we need a robust root cause analysis, and that requires end-to-end traceability. But where does traditional traceability fall short? And this webinar is titled Powder to Pack for a reason, right? We're thinking the full process, and this really speaks to that traceability message.
Yeah, there's so many different methodologies of traceability of the cell manufacturing process. I think one thing I like the analogy of discrete manufacturing assembly of physical tangible things. QR codes or barcode scanners or something that tracks a physical, widget to a production stage at a point in time is a really easy and proven way to track and trace, right? But that only gives you insight as to like the physical traceability of step to step, piece to piece. This was added, this is now your bill of materials because these things were introduced, right? What's missing from that is all of the time domain data associated with that transformation. And I think a lot of that data is really what is available in manufacturing, and that should be taken advantage of. And I think Jared was going to walk us through that.
Yeah, so if we think about all of the data that's getting collected here, so especially the time domain, people forget about the time because again, the cell sits there, it's aging, things are happening inside of it that you don't see. We're going to think about, again, like if the defects that we're going to pick what to trace, what's the process, what's the design, what's the equipment. So those need to be traced, all that data, and over time. We're going to trace it over time, and then we're going to switch to the cells and then trace those over time. So if we think about the process, we're going to be collecting all of the process information about mixing, as well as the environment that it happened in, and then the time that it happened. We're going to be collecting the same information about our mechanical processes here with the cell assembly. What were the mechanical processes happening? What was the environmental condition? What time did it happen? And then the formation and aging, that's like the electrical interaction with the battery. So what was the, charging cycles and discharge cycles? What was the actual cell performance that came out? What time did it happen? And what was the environment? The environment's less important there, but well, for things like what was the temperature of the cell, if we keep it warm or cool, maybe it charges or discharges better. And then of course, if we put it in pressure, but being able to collect all this information and then trace it back to the cell to say, okay, this cell that came out at the end, this one was great, but the one right next to it was not so great. What was the difference between these two? That's very important. For example, maybe the cell right next to it, there was the 8-hour shift and the people came in and out and the doors were opening and closing. And so for just a brief period of time, the moisture in the room spiked. So that would be the environment, and we'd need to collect that information. So that would explain why the cell right next to it was not so great, because it was at that 8-hour shift change. And so it got moisture contamination. So that's the sort of information we need to be able to trace and track and connect to the battery, so that at the end we can know, why do we have good cells? What happened with the not so good cells?
Yeah, and I love how this slide really sums up, it's not just the cell manufacturing process to look at, but also like the building, the processes, the facility infrastructure, who is working on the line at a given time. Like there are so many variables that go into the ultimate performance of the cell, let alone that can cause issues. Having an eye on like everything to a granular detail is key, right? That's really the only way to go. You got to know. And I've run into the case where we all of a sudden had bad performing cells, and it was like, what just happened? And we didn't know until we were actually like cycling them. And then it turned out a supplier changed a raw material on us, but that took us a few months to figure out. And that was on a smaller scale than a Gigafactory, but you still have that time is everything when you're producing cells.
Yep. And that happens as well in Gigafactories. The supplier, needed something and they added a little extra in that they had left over. So
Yeah.
it happens.
It happens for sure. And tell us about these different tools that people can use on their lines to help with those key quality measurements.
Yeah, I think there's a few examples here that we as Honeywell deliver and have been delivering for some time, right, to improve quality in the production process. So I mentioned, the challenge of translating, transactional data and then including time domain data associated with those physical transformations is a huge challenge, right? So if you think about the cell manufacturing process, a lot of times, not always, but it starts in a batch process, right? And then that batch gets transformed into a roll of material, right? So you're going from batch to a roll process to mechanical assembly. And so that transformation and packaging all of that data together is very difficult. And so some ways that we help address that is by implementing more measurement and more control to give you a better understanding of how things are performing in real time. And so one example is measuring continuously your loading or your coating weight measurement of the active material, or even the ceramic insulating coating on the cathode. And so there's always a specification. So how many milligrams per square centimeter you need to put of cathode on each side of the aluminum current collector. And same thing on the anode side. How much graphite or silicon or something else you need to put on both sides of the foil. And so instead of cutting a piece off and taking it into the lab and measuring it on an analytical balance and removing the raw material with NMP and then weighing the foil again and then determining based on the area that you cut from the electrode, you then know the weight delta. You can tell I may have done this in the past a few times.
I can hear that, and I've done it too. So
instead of doing all of that, you can have an inline sensor, such as our 8080 scanner with beta or X-ray sensor that tells you this information in real time.
yeah.
And so not only do you get a single point, but you get a good idea of the entire parent roll you've manufactured of the loading from start to finish. And so if things are deviating, you can make changes in real time to the slurry, to your coating conditions, or to the calendar press, which brings up another example. Instead of cutting off a piece of electrode, taking it into the lab, using a handheld mic to measure, the thickness, you can have an inline non-physical contact sensor tell you the thickness in real time as you're calendaring the electrode. And so not only are you getting real-time feedback, you're not compromising the electrode by making physical contact with that electrode. And so based on that, that's other data you can feed back to make process changes. And bringing it all together is, what if you could automate the coating process, right? So what if your slot die is dynamic instead of static? And so that's kind of that third example that you saw on the screen, was the slot die is able to dynamically respond to non-uniform coating based on data that's coming from the loading measurement that I just mentioned. You can feed that data through a control algorithm, so the slot die makes adjustments in real time. And so these are just some examples of how we've been doing it, how you as the viewer could be doing that. More measurement gives you more control, which ultimately results in a better quality cell.
Wow. Yes. JR, yeah, go ahead.
Yeah, it's awesome. I mean, you could shim if you wanted to, you still can, but wouldn't it be great if you can just auto code it and never think of it again? It will react in the time that it takes for the signal to see it and go back there. It's within milliseconds if you want. So the other ones here that below, there's also visual mapping, which is really lovely because it's like a role mapping process that has cameras that look at the roll and see if there's any defect and feed that information into the system. So along with that roll mapping, we've got defect marking. So you can put little QR codes to say, hey, there's a significant defect here, which is great because then you don't stop the process, slice out a piece of foil and then keep going. You just mark it and later you can remove it. These are the sorts of full roll mapping and defect marking that makes things fast and automated, and you can respond quickly. It's so much easier when you have all that data.
Yeah, because I can imagine even if you're getting a signal, then you're going back to your line and going, okay, where was that? So having that marking, having it be non-destructive, that is so critical. And when it comes to managing, this is a lot of data you're gathering on this process. And so collecting all this data, navigating through looking at it, tell us more about how this is handled with your systems.
Yeah, data management, especially at scale, is very difficult.
Yeah.
Right? So as you mentioned, Jill, you have these results, and then you have to go back and manually figure out where it was, when it happened, who was there, where was the process step, what batch was it, right? So the objective is to do all of that using a digital solution, right, versus doing it manually, and then doing things offline and like a typical PC type of program. So it's really industrial software. From us, it's our battery MXP platform, which you can think of as your operating platform for manufacturing. So the ability to see each production stage, each production line, if there's multiple lines in a facility, and then also the ability to look at manufacturing in progress, and then also be, again, the mindset of being proactive, seeing what's upcoming, seeing what's being planned. So if there's issues in one production stage, you can be proactive because you know things are planned to be in formation. But let's say there's an issue in formation. So since you know you're about to be sending 10,000 cells into formation, aging, and testing, you can then go in, resolve the issue, so there's no bottleneck in the process. You can kind of have that continuous throughput of trays and cells not being stop and go, but being transferred between production stages.
Yeah, and looking at this process on the screen here, the manufacturing process of a cell, so many both continuous and discrete processes. We were talking about traceability earlier, and JR, I would love your take on why aren't QR codes enough for full traceability?
So a QR code is the first step. So after that QR code, it needs to actually be connected to the full amount of information, again, about our materials, our process, our design, and our equipment, and the people. We should mention, we consider them the process, and the environment. So that has to lead to deeper data. And we need to be able to link it as it goes through from that powder to the individual cell to what cell goes in the pack, so that each one is a cumulative building of the last one. And this is especially important because we want to stop that propagation of error. If you get one error here, that's both it's less yield, we hope, if we catch it, but also it could actually be building up as we go along. So let's say, you've got two mediocre cells. Well, the pack ends up with a bad spot or a bad module in it. Maybe it's just because those two mediocre cells combined is bad. But same thing with defects. You've got two kind of low grade defects, but together it makes a worse performing cell. So we want to be able to catch those, and we want all that information to come through so that we can figure out what's really causing the errors or the low cells. And that means that we need lots of sensors, and we need to be able to connect, as Alec said, we need to be able to connect the data from every single step in order to see the whole process and in order to get that feedback loop.
Yeah, I love that. And I mean, this dashboard is everything, right? Being able to view this in real time, being able to link it to where it's happening on the line, and catching and visualizing deviations is super important, right, Alec?
Right, capturing deviations, just like JR mentioned as well, but
Yeah.
not every deviation is catastrophic,
Hmm.
right? So you always have to kind of ground yourself, right? So every production stage has a specification. It has a control limit you try to operate within. But then you also have a specification limit to where if you deviate from the control limits, maybe that's the warning here. Again, every, end user and cell manufacturer does things a little bit differently. So you want to capture deviations from control limits, because if there's a trend of equipment always deviating from control limits, usually there's a maintenance issue or, things like that. But when you start to deviate from your spec, that's when things go sideways. And so that's what you're seeing here. And so you capture the deviation, but then you also have the ability to categorize the deviation. Is it low risk, medium risk, high risk? Is it a warning, or do we need to implement a corrective action yesterday to make sure this doesn't happen again? And so this dashboard here is an example of how we at Honeywell do that. So you can configure the dashboard, configure your spec limits, configure your control limits. You get to decide, what is high risk and what needs immediate attention. But at the end of the day, everything can be seen in one place and not have to sift through data offline to make decisions.
Yeah, that's so important. And I love how you pointed out that yes, there's going to be some deviations, but they have to be according to your specifications, right? And speaking of specifications, traceability, all these things, there are global standards out there, right? And there's compliance that companies need to think about. What global trends are there around the policies and regulations for traceability in the battery industry?
Yeah, one thing I've been reflecting about, leading up to this webinar was if you look at the quality of lithium-ion cells that are made today are so much better than they were even 5 years ago, right? They have better quality, they have better performance, they have lower cost, right? And they have better traceability than we have had historically. So I think everybody's working towards, early 2027 as the go live for things like the battery passport in the EU. And there's things like that globally that are being rolled out. And there's so many different quality standards that have been implemented, whether it's the defense industry or automotive or space and aerospace. There's always quality standards that really tell you where you need to be, but not always how to get there. So it's these must be your standards. You must have these. You have to demonstrate this degree of traceability, right? But what do you use to do that is really up to you, and that's where we can help out, right? Of course, there's different tools and technologies from many different sources, right? We're just one of them. And it's up to you to decide what sort of technologies are implemented to ensure you meet the ISO standard, to meet a passport standard or something like that.
Yeah. And the regulations, they really just guide like what to achieve, not like how to achieve it, right? For that, you have to get creative with your chemistry, your process, everything like that. How does Honeywell support this continuous improvement for companies?
Yeah, so a lot of what we're doing here is that kind of Six Sigma continuous improvement quality control process so that you can continue to measure and you can actually tighten your tolerances. Maybe for some of these cells, you actually want the first couple of steps to have 8 Sigma so that there's less cascade effect or less propagation of error down the line. So you actually might want to tighten your tolerances and your control up at the beginning. Obviously you want to do it everywhere, but you can work on that. So we can work on, let's improve your yield in the first couple of steps first before we worry about the next ones. Or if the next one, like the electrolyte, feels quite expensive, maybe we want to start there and we get the yield and the quality up there. But that's the sort of like, let us help you trace your defects, find your defects, trace your defects, measure your defects, and what gets measured gets improved so that we can start improving. And it's very much, you might think of like, I think of like an old car where if you, like think of your first car. If you have an old car and you fix something in, let's say the engine, right? Now it's working perfectly and it's putting out more pressure maybe on the cooling system. And then the cooling system starts to go, not because it was terrible, but because now it's having more pressure put on it. It can be the same thing with manufacturing. So once you fix one part of your manufacturing and it's great, you can have other things start to show up that you didn't see before because there wasn't it wasn't as obvious, there wasn't as much pressure on that part of the system. So it will be a continuously improving process. We get everything to a certain level, we step up this one, and then we have to bring all the rest of the steps up to the new level. But that's normal and that's wonderful because by the end everything's in control and it's all working perfectly.
Yes, and we've covered so many incredible topics about battery quality today. As we're wrapping up, we want to think about, we looked at that curve early on in the presentation, and now we can think about applying all these things we talked about for traceability, for detecting defects, both in the process and latent defects. So tell us shortly, just what would you say overall with this new approach with Honeywell? How can you make sure that you're supporting quality cell production?
Yeah, I think, it's always a collaborative discussion, right? So going back to the question you asked JR, it's always collaborative and it's problem solving, right? So what is the problem and how can we help solve it, right? And it's really a bi-directional exchange of ideas and kind of spitballing, and different tools are available, and how you configure them and implement them is how you implement a more robust quality program, I think one thing we, touched on, briefly was, how do you utilize software, and then how do you utilize things like machine learning to aid you? And so there's more tools that come out over time. And so the more data you have available to you, the quicker you can make decisions, the quicker quality corrections can be implemented. There's many tools that, even we have available that can help do that. One example being our TrackWise quality platform that's used in many industries, battery being one of them, medical and life sciences being another one. So at the end, just to kind of call back to the original capital project journey, right? This is how you can de-risk the project. You implement different programs along the way, more planning up front, more problem solving and bidirectional exchange of information and ideas is how you shorten your break-even point from 5 years to 3. How you, instead of being, walking through a canyon of despair, maybe it's a meadow or a small valley instead, right? So I think, that's really the objective, is being more proactive, getting to the break-even point sooner than later, and ultimately producing a higher quality cell than you would have otherwise.
Absolutely. Yeah, JR, do you want to add to that?
I think Alec covered most of it. Probably one of the things we might suggest is, when you buy your equipment or when you start with a new process, bring us in then at the very beginning with the control system so that we can help you plan what is going to be the best, most effective measurement tools and what are going to be your feedback control loops and how do you want to measure it, so that at the very beginning we can help you from the start, especially like both that valley of despair, but then also, just learning to control your equipment from the beginning. So, yeah.
Absolutely. When you have those very brilliant partners who have done it before, they have that experience that means more than reading a textbook on how do you make a battery, right? To actually live it and learn it and see and learn from mistakes of the past and build on that, right? That's what innovation's all about, is right, standing on the shoulders of giants. I love that phrase. So thank you both so much for joining in with us and sharing your expertise here today. This has been such an incredible conversation. And to the audience, please do reach out, go to that QR code. And when you go there, there will be actually a form on that page that you can fill out and submit and say that you saw this webinar. We would love to hear if you watch this and you have any questions for Alec or JR. And for you too, what's the best way for people to reach you?
Definitely put comments and questions, in the video. We're happy to answer them, over time, no issue. Otherwise, please send us an email, reach out on LinkedIn. Happy to connect and talk further.
Awesome. Yes, your emails are right there on the slide, I see. Excellent. Well, thank you both so much for joining me today.
Yep. Thanks again. Take care.
Thank you, Jill. It's been a pleasure.